the first thing let's talk about is this point where the axes meet has a name. Origin. Good. So that's the point 0, 0. Okay. And so 0, 0, right? Coordinates are x, y. Okay, those are our coordinates. And what do we call the vertical line that goes through 0, 0? The y axis. And what do we call the horizontal line that goes through the origin? The x-axis. Good. Our quadrants also have names, I guess, right? What is this quadrant right here called? Quadrant, yeah, very creative, right? Quadrant 1. Then we move what direction? Is quadrant 2 clockwise or counterclockwise? Left, counterclockwise. Quadrant 2. Quadrant 3. And quadrant 4. Usually we use Roman numerals when naming the quadrants. 1, 2, and so you need to know some Roman numerals. So what else do we need to remember? That's Cartesian plane, right? So we're going to use the Cartesian plane a lot. X is our input. And we also call it the independent variable. So do you remember talking, I don't know if you've heard about, I think it's called function man, or something like that. So if you input your x, what comes out? Your y is the output, or the dependent variable. That's why our coordinates are x comma y, right? Whatever x is, then y happens as a result. X is the independent, y depends on x. Y is the output. So y always depends on what the x is. Did you talk about this in grade 9 a little bit? Not so much. These are probably new terms, right? Independent, dependent. In science, you call them manipulated responding, right? So in science, x would be your manipulated variable, and then y responds because of x, right? Same idea, different terminology. And you're going to find in this unit so much terminology. Yay. So we got to just learn our terminology. So there's a chart here you're going to have to maybe make on the side, and we're going to graph y equals 2x plus 3. So that's an equation. Why is it an equation? It has what? An equal sign, right? So let's choose some x's. I'm going to choose -2, -1, 0, 1, 2, 3, and 4. Okay, so those are my independent variables, the ones I'm technically manipulating. So how do I get the y value if x is -2? Pardon me? Yeah. Just kind of solve it? Exactly. So by solving it, you mean 2 times, what's the x value? So we're going to use this equation. So we have our input. Our input is -2, and we want to output y. 2 times -2 plus 3, what does that equal? -1, because -4 plus 3 is -1. So as an ordered pair, that would be -2, -1. So we can plot that. 1, 2. Your graph looks a little different. Okay, so x first, then y. So x -2 is 2 to the left, down 1 for y. Easy? Okay, -1. 2 times -1 plus 3, what does that equal? 1. So this would be the coordinate, -1 and 1. Can you fill in the rest? Yes, okay, good. Fill in the rest. Solve for the rest of the y values and then plot them. What did you get for 1? X is 1. 5. Good. What did you get for 2? 7. Do you see a pattern? You should. What are we going up by each time? +2. I wonder if that has to do with anything with that number in front of x. Maybe. Okay, so you should have 9 and then 11. I don't think 11's on yours. Okay, now if it's not a contextual problem, it's just an equation, okay, then we join the points. So if it was actually contextualized problem, do you know what I mean when I say contextualized problem? Just sounds like fancy words, doesn't it? Yes. Okay, for example, if we were graphing number of ticket stubs and the money we make, okay, would you have half of a ticket stub? No, you wouldn't. So like in a contextualized problem, like a word problem, we have to ask ourselves, do we connect the dots or do we not? Does that make more sense? So if it's actually like word problem, then you have to ask yourself, do we actually join these points? But if it's an equation, then we do. And if you're lucky, you have a program that makes a nice line. In real world, we call those rulers, I guess. Smart words. Okay, so that's where rulers are nice. Honestly, I recommend you get a ruler because you're going to be drawing a lot of lines this next 3 units. So you have a ruler, it'd be helpful. Okay. Now, just a little side point, side thing. 0,3 is a special point. I called it special, quotations. It's not actually called a special point, but why is it unique? What makes it special? Yes. Hey, it's the constant of +3. Oops, I'm still on lines. Okay, the constant of +3, which you can't see it there. Okay, so that's interesting. And also, what about it is interesting? It's a point that where it crosses what? Yeah, the y-axis. And so we actually have a name for that, which we'll be talking a lot about, and that's called the y-intercept. Because it's where it intercepts the y-axis. Make sense? Okay, and it's going to be really important. So we're going to be looking at equations that look like this a lot in the future. So yeah, a lot. Hopefully this lesson doesn't go too long, but it might. So I'd like you to grab your workbooks and turn to page 389. Okay. We're going to go back to those other notes in a little bit, but for now, on page 389, it says complete the following by writing the coordinates of the points represented by the letters on the grid. So this should be review, right? Easy? Can you just quickly fill this in? Like it's almost insulting, hey? You're like, I know how to do this. Right? Write the coordinates. So figure A would be 2 and 4. Good. X and Y. Alphabetical. What's B? Okay, -3, 0. You guys finish the rest. And finish the rest, like, answer A, B, C, D. This is a good little review activity. Yell it out. 6, -3. What was D? 0 and -3. Good. Good. And then 0. Oh, yeah, 0, 0 for the origin. It's always called O. Okay, coordinates of the point in the second quadrant. So 1, 2, 3, 4. That would be -2 and 3. That would be E. Okay, in quadrant 3, what's the coordinate at the point in quadrant 3? Which one? -4, -3. And then first quadrant, X's and Y's are both positive. In the second quadrant, what? X is positive, Y is negative. No, no. X is negative, Y is positive. Third quadrant, X is negative, Y is negative. Good. And then last, fourth, positive, negative. Beautiful. Okay, toothpicks. 3 toothpicks are used to form a triangle. A second triangle is formed by adding 2 more toothpicks. Third triangle is formed by adding another 2 more toothpicks. And the pattern continues. So in the first, how many toothpicks were in the first triangle? You needed how many? 3. How many did you need for the next one? Count them. 1, 2, 3, 4, 5. Okay, how many for the next? 7? 1, 2, 3, 4, 5, 6, 7. How many more are we adding each time? 2. So we're starting with 3 and then we have to add 2 each time. Okay. So we have this chart. Complete the table. So we had 1 is 3, 2 was 5, 3 was 7. What would 4 be then? 9 and 5 would be 11. We need to add another 2 toothpicks to make another triangle. So we already use an existing side. Okay, represent the data. So plot the points. So the question is, when you have a table, which one's X and which one's Y? X is the independent. Which one's independent? The number of triangles. So the first one is always X. The second is always Y. The input, output, right? So the number of triangles is what? Is that going to be independent or dependent? Independent. X is independent variable. And then the Y would be dependent. So if I want this many triangles, as a result, I would need this many toothpicks. Oops. Okay, let's plot them. So 1, 3. 1, 2. So they already have the variable t for us, for x. Okay. 2 is 5, 3 is 7, 4 is 9, 5 is 11. Okay, explain why it does not make sense to join the points in a straight line. This is what we were talking about before. Why does it not? Yeah. There's no partial triangle and there's no partial toothpick. So this is an example of what we call discrete data. So discrete data is where we do not connect or join the points. And you basically just have to ask yourself, is it possible to have half of the variable or a decimal of the variable? Can I have half of a toothpick in this problem, in this type of situation? No. So we can't have a partial toothpick or triangle. Okay. Describe in words the relationship between the number of toothpicks and the number of triangles. Okay, so what's the relationship between 1 and 3, 2 and 5, 3 and 7? What are we doing to our number of triangles? Yeah? Doubling it and adding 1. So the number of toothpicks is 2 times the number of triangles plus 1. Or you could say 1 more than 2 times the number of triangles. So let's write an equation. Yes. Okay, so we want to use the variables p and t. So instead of x, you do 2t plus 1 equals p. Yeah. And use the equation to determine the number of toothpicks if there is 27 triangles. So what did they give us, t or p? Triangles or toothpicks? Triangles. So they say t is equal to 27. So we plug it into our equation. Whenever we substitute into equation, we use brackets. I don't know if you can see that at the back. 2 times 27 plus 1, what does that equal? 2 times 27, you could do that in your head. 54 plus 1, 55. Good. Use the equation to determine the number of triangles if there are 83 toothpicks. Yes. 83 minus 1 divided by 2. So we sub in 83 in for p. We could first subtract 1. Right, Jayesh? And then you get 82 equals 2t, divide by 2. So how many triangles? 41. Oops. 2. Good. All right, grab your notes. Where we were just at. Yours are in a different order than what I have up here. That's okay. I'll go with what you have first. Okay, have you ever heard the word set before? Other than volleyball? Or, right? Yeah? It has 83 definitions if you look it up. Yeah, there's a lot of definitions for the word set. So you probably heard the word set before. Yeah. Okay, so in terms of graphing and relations, we're going to define it as a collection of objects. Collection of objects. So, example. We talk about the set of all positive even numbers. Oops. Numbers? Okay. 2, 4, 6, 8. Okay, that's an example of the set. Those are set brackets. They're squiggly. They look like this. Isn't they pretty? Students have a hard time writing set brackets. It's really funny. Do your best, okay? Do your best. Is it too small? Do you want me to make it larger from people to back? Hey, Matt? You're good? Anna? Larger? We're good? Okay. All right, so an element is an object in the set. In a set. So for example, 2 is an element of the set of all positive even numbers. It's an object in a set. So a very minimal definition of a discrete variable. I just talked, remember we just looked at a discrete discrete data where we can't join the points because you couldn't have partial of it, right? So a very limited definition could be if you have limited x values. We'll talk about that definition more in the future. Whereas continuous, what do you think continuous would be versus discrete? You can have all values. Yeah, you can have decimals and fractions. The actual definition of a continuous function is one that you can draw without lifting your pencil. Like that's actually the definition. You can draw it without lifting your pencil. Okay, so every value of the independent variable can exist. I don't think you can see that, eh? There you go. Every value of the independent variable, which is x, can exist. Sorry, can draw without lifting your pencil. If it's a graph, okay? If it's a continuous function. It says pencil. I know it doesn't look like pencil. I need to work on my penmanship up here. There. Okay, relation. I don't know if you've noticed this, but our unit's called relations and functions. And so expect to need to know the definition of a relation and a function. Okay, so let's talk about a relation, and there's more examples on 399 of your workbook. So it associates the elements of one set to the elements of another set. I'll give you an example in a second. And we're not going to define function today. I'm actually going to leave that for another day. Okay. So for example, if I relate comparing coin names to coin values. Give me an example of an ordered pair in that relation. Give me nickel, 5 cents. Okay, what's another one? Dime, 10 cents. Any other ones? Yeah? Oh, that's a long one to write. Royal Canadian 50-cent coin? How's that? Any other ones? Quarter, 25. Okay, dot, dot, dot. Okay, that's an example of a relation. You need two things, right? Relation, relating two things together. Yep. Okay, so there's some... I thought somebody was going to give me another language. Like, because I didn't say in English. Yeah, that's exactly. Ruby. All right, so reading a table. Just to review, x is always first, then y, because x is your input, y is your output. X is the independent, y is the dependent. We are going to spend 2 days on this word and this word. Domain and range. So very briefly, domain is the elements of the first set, or of the independent variable. Whereas range would be the elements of the, or in the, or yeah, of the dependent. Lots of terminology, don't you love it? It'll get better because we're just kind of like knocking a lot of them out right now. Okay, turn the page. Okay, northern communities can be associated with the territories they are in. Consider the relation represented by this table. So we have communities and territories. You guys are with me? Yeah? Okay, which one is the dependent variable? Good, you list dependent. Okay, which one is the independent then? Obviously, process of elimination. Okay, let's describe this relation in words. How could you describe this relation in words? These communities are located in these territories. How about that? These communities, I have an extra like bump on my M. That's okay. Are located in these territories. I kind of skipped over something on the previous page, and that was talking about how we can represent relations. So one way we can represent a relation is with words. Just did that. Okay? Another way, a table. Another way, ordered pairs. Okay, so let's write the ordered pairs. So this is a set, so we're going to open it with set brackets. And what's the first ordered pair? Hey River and Northwest Territories. Oh yes. we can shorten it a bit if you need to. Okay, I'm gonna say this wrong. Iqaluit? No, I said it right. Iqaluit, right? Yeah. Yeah, thank you. Comma. Oh, here we go. Nineveh. Who wants to take a stab at the next one? Naniscavit? Naniscavit? Oh, thank you. Shortening it a little bit. I've never heard of Old Crow. Have you? Have you? Hey, isn't that... I should not be Canadian. I'm just embarrassing myself. Oops. I need to go look at a map today. It's in Yukon. Whitehorse. Yukon. Okay, notice how there's commas between each ordered pair as well. And then Yellowknife, Northwest Territories. Okay, so we can represent relations with words, with a table, ordered pairs. Now we're going to learn about an arrow diagram. Okay, so yes, we can use arrow diagrams, and we need to practice because it probably will show up on a quiz or a unit exam, and you need to recognize them. So with an arrow diagram, our independent variable goes first because that's our input, and our dependent goes second. Okay, so we only write an element once. You never write it twice, even if it appears twice. Okay, does that make sense? So is there any repeating communities? No. So we just write each one. Hey River, Iqaluit, Naniscavit, yeah. Old Crow, Whitehorse, and Yellowknife. Yeah, I'll go. And then, how many times am I going to write? Will I write Northwest Territories? Once. Now, usually you go alphabetically, but I'm not going to be too picky about that. Nunavut, we're only going to write once. And then what else do we have to write? Yukon. Okay. Now, on the very top, we have an arrow showing that these are related, and we write the relationship on top. So basically, what is the words connecting these two sets? I could say, hey River, blah, 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 Northwest Territories. Is located in. Beautiful. You actually understood my gibberish. It's amazing. Okay, is located in. And then we draw our arrows. So, hey River, we're going to connect to Northwest Territories, Iqaluit, none of it. Meniskevich, none of it. Old Crow goes to Yukon. Whitehorse is Yukon. And then Yellowknife, Northwest Territories. That's it. Pretty simple, right? There's one other method which doesn't make sense in this example, but there's another way to represent a relation. What's the other way? We have a table here represented. Have a map arrow diagram. A graph. So that's common, which is like makes sense. We're just learning about graphs. Is a graph, okay? So here is an example of a graph. How are we doing for time? Ooh, we're doing okay. Let's try and speedy this along. Okay. Oh, well, yeah, let's move on. The graph below represents a jogging record. So compare the speed and direction of traveling before and after the rest period. So let's talk about this graph. There's a lot to talk about here. Okay, well, first off, what are the two variables we have relating each other? Relating what to what? Time to distance traveled. Okay, so this is a time distance graph. Now, if you have studied some physics, you're in luck because you're going to have an advantage. Anyone here in science 10? Yeah, you done this? Oh yeah, so you haven't yet. You will. Look at that. But if you have a huge advantage because you talk about time distance graphs and velocity time graphs, acceleration time graphs, right? And that's important in math too. So we're relating these two. So at certain points we're not moving, and at certain points we are. So where in this graph are we resting? We're not moving. Yeah? Okay, so Tristan, Mr. Physics, 20 to 40, right? Why?
Because there's no movement at all, and it's just in a straight line as the length and distance.
Not just a straight line, because these are straight lines.
But in a
horizontal line, so on a distance time graph, because is his distance 2 kilometers changing? No, he's still 2 kilometers away from wherever he started. And so he's not moving. So this would be no motion, right? He's not, no movement. And what's happening, it says distance from home. So what's happening from 0 to 20? Is he running towards home or away from home? Away from home, stops for coffee or he's exhausted or he's passed out. And then sprints home. Does he start off at home? No, he didn't. He actually started 1 kilometer from home. Right, so these are the things that we need to be able to do to interpret this. So, okay, so let's talk about from 0 to 20 minutes. How could we find his speed? Yeah? Speed is distance over time. Yeah, it's our distance over our time. And this is a very basic formula that we're using for constant, we're assuming that our speed is constant. We're not accelerating, which, let's be honest, in real life, that's not realistic. It's very hard to maintain a constant speed. Even if you set cruise control, your vehicle is going to go a little bit above, below, right? The actual reality of constant speed is hard to maintain that. But if we're really actually doing averages, then we can talk about a constant speed. So how far did I travel in the first 20 minutes? So I went from 1 to 2. 1 kilometer in how long? How long does that take? In 20 minutes. So 1 kilometer for 20 minutes. So 1/20th, we're not going to divide that. We're just going to talk about, and his direction is away from home. Okay, we're not going to change this to hours or anything. Yeah, we're just going to leave what is 1 over 20? It would be 0.0. 0.2? 0.0, that sounds right. Yeah. 0.05 kilometers per minute. Okay, what about from 20 to 40? What's his speed? 0 kilometers per minute, and he stopped. Right? And if we use distance over time, we'd have 0 divided by 20, and 0 divided by 20 is just 0. Okay, what about 40 to 50? minutes. Speed equals distance over time. How far did he travel there? 2 kilometers. And in how long? 10 minutes, which is 0.2 kilometers per minute. And what direction is he moving? Towards home. Okay. We're almost done. Let's look really quickly at the next page. And what I want you to do is match. So I'd like you to read there's 4 scenarios, 4 graphs. Very popular unit exam question or quiz question. Match each scenario with its appropriate graph, justify your answer. So the height of a bungee jumper after. So we're assuming like this one would be graphing height versus time. All of these are on time. So height versus time, vertical growth versus time, temperature versus time, Calgary's mean temperature versus time. So given the different, read through them and see if you can match each graph with each situation. And we'll go through it. Okay, let's go through them. Which one are you certain of? The jumper, the height of a bungee jumper after a jump. Anyone bungee jump before? Not yet? Anyone want to? Yeah, you guys are, the idea of just being like flung around by a cord. I'd rather parachute. Yeah, right? My dad actually, skydiving, my dad actually had like 41 jumps under his belt until my mom made him quit because there was a couple times where his chute did not open. Yeah, one time specifically, and he broke like every bone in his body. It's amazing he's alive. And then they're like, well, you do. He was like a skilled one. It's amazing he's alive. So that's a side note. Cool story, hey? Bungee jumper, A. Yeah, it's crazy. But I would still try it, even knowing that. The vertical growth of a tree. Anyone want to take a guess at that one? Yeah? Graph A. Okay. Is that the best graph to show it?
Yep. Yeah.
It's not the greatest, but it is the best one there. I feel like it should plateau, right? Like it should actually be like more like this. So I'm kind of not impressed with my graph I gave you. I'm sorry.
Yeah,
they do keep growing a little bit, but they kind of plateau-ish. Oh, it does kind of slow down. Okay, that was B. Okay, graph, let's say the temperature of a cup of hot chocolate as it sits on the table. Graph B, it's warm and then it starts to cool down and gets to room temperature. And then last, Calgary's daily mean temperature. A. Graph, that would be D, right? Because in like January, the average is below 0. This would be like summer. It's above 0, the average. Back to winter, right? December. Okay, easy enough? So let's just talk about a little bit of physics here. If we have a straight line that has a constant rate of change. So be careful, I'm not necessarily talking about a distance time graph. I'm just saying in general, our rate of change, which we're going to actually call that slope one day, and interesting enough, the whole calculus course is 100% based on rate of change. Everything about pretty much, like almost everything is rate of change in calculus. So that's what you're really building up to, is this idea of slope and rate of change. Because change is constant, right? That's one thing that we know is constant is things change. That was kind of a philosophical statement. But so rate of change. So if we have a straight line, we have a constant rate of change. If we have a curved line, then the rate of change is not constant. It's changing. Like this would be something, for example, for this distance time, it's slowing down, right? And then no rate of change is a horizontal line. And that's why in distance time, That horizontal line is when we were stopped. There was no rate of change. Okay? All right, so what's your homework for today? Well, that handout you have, I recommend the handout you grabbed on the front table that tells you what we're doing each day. So our quiz is next Friday, and then the Friday after that is our unit exam. Kind of works out nicely. And then we're into December. Yeah, December's a short month. We have Christmas break. So what's our homework today? We are at page 392. Oh yeah, I was going to recommend something. See this sheet? Remember your formula sheet I gave you with a page protector? Okay? The side that has all the surface area volume formulas, you don't need those this unit. Why don't you slide this in there so you always have like your homework sheet accessible instead of losing it. Okay, so circle the following. 1, 2, 4, 5, 8, 9, 11, and 12. And page 406, a lot of these are easy and quick. 1 to 3, 7, A, B, C, and 8. I do have like some AP scenarios that we will look at this unit. I want to give you some time for homework, so let's get started. Okay? Gurjat, you're not listening. You listening? It's okay.